So you want to break into embodied intelligence robotics. Let me guess what's stopping you. You've probably asked yourself the same question 100 times. Should I start with theory or should I just build something? If I jump straight into a project, I can't even read the tech stack. But if I go back and grind through math and circuits, I feel like I'll never actually build a real robot. Today, I'm going to cut through all that noise and lay out the clearest possible learning path for embodied intelligence. Here's the key insight most people miss. If you're a total beginner with zero background, here's my advice. Just start building. Seriously. Get your hands dirty immediately. But if you already have some foundation and you're aiming for a career in this field, if you want the high-paying jobs, then your path looks completely different from what everyone else is telling you. Let me explain why. Embodied intelligence has a fundamental problem that nobody talks about. What is the complete tech stack? You cannot figure this out just by building projects. You need systematic knowledge. Now, I'm not telling you to go back to college and suffer through advanced calculus and analog circuits. That's not what I mean. I'm talking about laser-focused learning of the core concepts and mainstream technology pathways that actually matter. For example, simulation software. Take NVIDIA Isaac Sim. You don't need to master it. But you absolutely must understand what engineers actually use it for. What problems does it solve? Why does it exist? Same thing with sensors and motors. Quadruped robot dogs. Biped humanoid robots. What does their mechanical structure look like? How do you estimate the torque required at each joint? What ranges are we talking about? This is the hardware foundation and you need to know it. Then there's motion control. What computing hardware does the industry actually use? What control algorithms are standard? Hardware like the Rockchip RK3588. NVIDIA GPU compute boards, you need to know these exist and what they're used for. Move up the stack and you hit control algorithms. What reinforcement learning approaches are out there? What open source solutions exist for the full stack? Ideally, you want hands-on experience with all the major approaches. Next comes interaction. Voice interaction. What open source and commercial speech recognition engines are available? What about speech synthesis? And when a robot runs large language model inference on device, what open source solutions do people typically use? You cannot figure all this out purely by tinkering. This requires systematic awareness across hardware, mechanics, software, and large model architectures. Now here's the good news. You can absolutely run these two tracks in parallel. Build your foundational knowledge while simultaneously going hard on practical skills. How? Find an open-source embodied intelligence project. Quadruped, biped, even just a robotic arm doesn't matter. What matters is that you replicate the entire thing from start to finish. Hardware construction, circuit connections, software debugging, data collection, behavior model training. When you can run the full pipeline end-to-end, that's when you've truly entered the field. And here's the magic. Even if you only add one small modification of your own, if you apply it to a real concrete scenario, that becomes your portfolio piece. Go deep enough on this, and it becomes the most powerful project experience you can bring to a robotics job interview. I mean, the kind of project that makes interviewers sit up and pay attention. And if you open source it, if other people start wanting to reproduce your work, congratulations! You now have a position in this field. Now let's step back and ask a deeper question. You've seen the viral videos. Robots doing backflips, robots running, robots performing incredible acrobatics. The first time you see these, it's genuinely stunning. Most people's reaction is pure amazement. They think, I can't believe robots have reached this level. But here's what I want you to think about. After the initial shock wears off, we need to ask something more important. Does a robot that can run and jump and backflip actually qualify as truly intelligent? Is that really embodied intelligence? Think about it. A robot can do a perfect backflip, but if it can't understand human language, can't comprehend instructions, has no awareness of its environment, and can't make decisions based on a task, then what do we actually have? We have a machine with incredible athletic ability, but it's not an intelligent agent. It's not what we mean by embodied intelligence. Let me give you the counterexample. You say to a robot, Please go to the living room, find the water bottle on the table, and bring it to me. What does true embodied intelligence need to accomplish here? First, it needs to understand human speech. It needs to know what a living room is, what a table is, what a water bottle is, and what bring it to me means. Then it needs to observe the environment. Find the table, locate the objects on that table, identify which one is the water bottle among all the other items. Then, it needs to plan its actions. How should it navigate to the table? How should the hand approach the bottle? Should it grab the body or the cap? Finally, it needs to execute safely. Look at the scene. There might be cups next to the bottle, books nearby. How do you avoid knocking things over? And when gripping the bottle, how much force is right? Too much and you crush it. Too little and it slips. This is your safety strategy. Here's the thing. This task doesn't look nearly as spectacular as a backflip. It doesn't make for a viral video. But for a robot, this task is dramatically harder because it's not about repeating a pre-programmed motion. It's about completing a real task in the real world. And this reveals the true challenge. The hard part of robotics isn't making machines move. The hard part is making machines that can perceive their environment, understand tasks, plan autonomously, and execute safely. That is embodied intelligence. So let me define it clearly. Embodied intelligence is about giving AI a physical body that can act in the world. A body that can perceive the environment, understand tasks, plan actions, and safely achieve goals. In this chapter, we're going to build a complete mental model of what embodied intelligence actually is. No algorithms yet, no formulas, no jargon dump. First, we build the big picture. We're going to answer 5 questions. 1. Why do we need embodied intelligence? 2. What exactly is it? 3. What are its core components? 4. Where is it actually being applied? And 5. Why is it getting so much attention right now? Let's start with why we need it. Traditional AI has mostly been about recognition and judgment. Give a model an image, it tells you whether it's a cat or a dog. Give it audio, it transcribes speech to text. Give it a medical record, it helps diagnose disease. Give it text, it translates, summarizes, answers questions. These tasks are tremendously important. They drove the entire AI revolution, but they share one characteristic. The input is information. The output is a result. Image in, category out. Text in, answer out. Speech in, transcript out. This kind of AI is brilliant at perceiving and communicating, but it cannot act. Computer vision can tell you, this is water. A language model can tell you, I'm thirsty and you should drink water. But what we actually need goes beyond that. We need to know where the water is, how to get to it, how to grasp it, how to move without colliding, how to safely hand it to a person. This complex chain transforms AI from a pure recognition problem into a real-world action problem. This is why embodied intelligence exists. We want AI to not just understand the world, but to enter the world and change it. This is a fundamental shift. Traditional AI asks, what is this? What does this sentence mean? What's the answer to this question? It's focused on recognition, understanding, and judgment. Embodied intelligence asks different questions. Where am I? What should I do next? How should I do it? What happens if I take this action? If I fail, how do I recover? Embodied intelligence is not simply stuffing an AI model into a robot body. I see people say that all the time. Just put AI in a robot, and you have embodied intelligence. Wrong. What it really means is creating an agent that continuously perceives its environment, continuously makes decisions, and continuously takes action. A closed loop of perceive, decide, act, repeat. Think of it as AI's evolution from screens to reality. The old AI was a system that answered questions. The new AI not only answers questions, it executes them. That is the significance of embodied intelligence. Now let's define what it actually is. The term might feel abstract when you first hear it. Don't worry, let's break it apart. Embodied. Intelligence. 2 words. Embodied means having a body, real or virtual. The intelligence is not floating in the clouds somewhere. It's attached to a physical or simulated form. This body could be a real robot arm, a mobile robot, a humanoid, a self-driving car, or it could be virtual, a simulated robot, a game character. The key is that the body defines what the agent can and cannot do. This is not a trivial detail. The body is fundamental. Intelligence means the machine can assess its environment, evaluate its task, and take appropriate action. Put simply, give intelligence a body. Let that body interact with the world and complete the cycle of perceive, understand, decide, and act. There are several key insights packed into this definition. First, the body matters. It's not an afterthought. A robot vacuum has wheels. That means it can move across floors and clean, but it cannot reach up to grab a water bottle from a table. An industrial robot arm can assemble and grasp, but without a mobile base, it cannot relocate itself. The body determines capability and constraint simultaneously. Second, the environment matters. Embodied intelligence doesn't operate in a blank void. It works in real spaces, homes, factories, warehouses, roads, hospitals, and these environments are complex, dynamic, and partially uncontrollable. Objects in a home are never in exactly the same place twice. Roads have pedestrians and vehicles in constant motion. The agent must adapt to its environment, not just execute fixed routines. Third, interaction is continuous. This is the biggest difference from traditional AI. Traditional AI is one shot. Input comes in, output goes out, done. Embodied intelligence is a loop. Observe the world, think, act. The action changes the world. Observe the new world. Think again, act again. It's a closed feedback loop. You're constantly looking, thinking, doing, and adjusting. So in one sentence, embodied intelligence is AI that acts in the world through a body, continuously perceiving and adapting as it goes. Let me contrast this with traditional AI more explicitly. Traditional AI excels at understanding information. Image recognition, speech recognition, large language models, multimodal models all produce outputs like labels, scores, text responses. These are hugely valuable, but their outputs don't directly change the physical world. Embodied intelligence is different. It must understand, then decide, then act. Traditional AI cares about cognitive results. Embodied intelligence cares about action results. Traditional AI answers what and why. Embodied intelligence answers how. And because it must complete full tasks, it needs the entire chain from perception through execution. It's not replacing traditional AI. It's building on top of it, adding a body, putting that body in an environment, and closing the loop with action and feedback. It's the bridge from understanding the world to changing it. Now for the part most people are waiting for. What are the core components of embodied intelligence? I break it down into 5 systems: perception, understanding and reasoning, decision and planning, control and execution, and learning and feedback. These 5 are not isolated modules. They're interconnected. Think of it this way. Perception is seeing the world. Understanding is making sense of what you see. Decision and planning is figuring out what to do. Control and execution is actually doing it. And learning and feedback is getting better every time. Let me walk through each one. Perception is the foundation. It answers the question, what's around me? Humans use eyes, ears, touch, and body awareness for balance and posture. Robots are no different. They use sensors. Cameras capture color and appearance. Depth cameras measure distance. LiDAR handles navigation and obstacle avoidance. Tactile sensors detect contact. Force sensors measure grip pressure. Inertial measurement units track orientation and motion. Let's use our water bottle example again. The robot needs to know, where is the bottle? What shape and size is it? How far away? Are there obstacles nearby? Has my hand made contact? How much force am I applying? If any piece of this perception is off, everything downstream fails. Wrong position estimate. You missed the bottle. Wrong distance calculation. Your gripper closes before reaching it. or crashes into it. Perception is not optional. It is the foundation. Without it, the robot is blind to the world it's supposed to act in. Next, understanding and reasoning. Now the robot has perceived the scene. But it also needs to understand the human's instruction. Bring me the water bottle from the table sounds simple to us. For a machine, there's a lot to unpack. Bottle is the target object. Table is the location. Bring it to me means grasp and deliver. And human instructions are rarely that precise. What if I say, grab the thing I was drinking from earlier? The robot needs common sense. Humans typically drink from cups and bottles. What if I say, clean up the table? That's not a single action. That's a high-level goal requiring task decomposition. Identify all objects on the table. Classify them. Trash goes in the bin. Books get organized. Dishes go to the kitchen. This requires understanding intent, applying common sense, reasoning about categories, and decomposing goals into subtasks. This is where large language models and multimodal models have been transformative. They give robots powerful language, understanding, knowledge representation, and basic reasoning. But here's the nuance. Large models are only part of the picture. True embodied intelligence requires converting that understanding into physical action. Understanding is necessary, but not sufficient. Third, decision and planning. After perceiving and understanding, the robot needs to figure out how to execute. Back to our water bottle. Step 1. Navigate to the table. Step 2. Position the arm. Step 3. Select grip strategy. Step 4. Close the gripper. Step 5. Deliver to the user. Each step requires computation and judgment. Which direction to approach from? What if there's an obstacle? What if the bottle is near the edge of the table? What if it's glass and fragile? Planning operates at 2 levels. High-level planning handles task sequencing. Get bottle, then deliver. This lives mostly in the understanding and reasoning system. Low-level planning handles motion detail. What angle for each joint? What trajectory for the end effector? This is the decision and planning system proper. It's the same way humans work. Big goal first, then fine-tune the movements. Fourth, control and execution. Planning decides what to do. Control makes it actually happen. And there's a real gap between knowing and doing. The system planned a path for the arm to reach the bottle. But the arm doesn't just teleport there. Every joint angle, every velocity, every acceleration must be precisely regulated. The gripper must control its opening width and gripping force. Without precise control, everything falls apart. Jerky trajectories, oscillating arms, wrong approach angles that knock the bottle over. Too much force that crushes it, too little force that drops it. Real-world control is incredibly hard because the real world is not ideal. Objects slide. Tables aren't perfectly flat. Sensors have noise. Mechanical parts have tolerance errors. Different objects have different friction, weight, and shape. So the control system must continuously adjust based on feedback. The gripper senses contact through force sensors. Is the object secure? Is it starting to slip? Increase force. Too much pressure. Ease off. Control turns the plan into stable, accurate, safe physical execution. Fifth, learning and feedback. An embodied intelligence system is not a one-shot, pre-programmed sequence. It needs to learn from failure, from success, from experience, just like humans do. Remember, learning to use chopsticks as a kid. You failed a lot. Gradually, you learn to control the force and angle. Robots are the same. First time it tries to grab a bottle and fails, it needs to understand why. Was the position estimate wrong? Was the grip point poorly chosen? Was the force too low, too high? The system analyzes the failure and improves for next time. Learning comes from multiple sources. Human demonstrations with labeled data. Simulation environments where the robot can safely try millions of attempts. Real-world execution feedback, where every success and failure is recorded. And large models or knowledge bases that help interpret tasks and generate better plans. Learning and feedback is what makes embodied intelligence not just a one-time performer, but a continuously improving system. It answers, how did I do this time? And how do I do better next time? Now let's connect all five. The full pipeline. Robot receives the instruction. Bring me the water bottle from the table. Perception activates. Sensors scan the environment, locate the table, identify the bottle, detect the user, map obstacles. Understanding kicks in. Pass the human's words. Extract the goal target is water bottle. Action is grasp and deliver. Planning computes. Navigate to table. Approach bottle. Grip. Move to user. Control executes. Every motor, every joint, every force precisely regulated. Learning evaluates. Did it work? If not, what went wrong? Store that knowledge for next time. This five-part cycle, perceive, understand, plan, execute, learn, is the backbone of everything in embodied intelligence. It's not one model. It's not one piece of hardware. It's a complete integrated system. Master this cycle, and you've mastered the conceptual foundation of the entire field. Now that we understand what embodied intelligence is and how it's built, let's look at where it's actually being used. 5 majeures applications demain. First, home service robots. This is the one everyone immediately thinks of. Robots that help with household tasks, fetching items, tidying rooms, cleaning, caring for elderly people, cooking. You give a simple instruction like clean up the table, and the robot must identify objects, decide what to keep versus discard, navigate, grasp, and execute the full workflow. Sounds simple to humans. For robots, it's enormously complex. Why? Because homes are not standardized. Every home has a different layout. Objects are never in exactly the same place. People phrase instructions differently. Objects can be partially hidden or occluded. Home service robots demand extremely robust perception, understanding, planning, and execution. Second, industrial manufacturing and logistics. Traditional industrial robots have been in factories for decades, welding, assembly, painting. But traditional industrial robots work best in fixed environments with fixed processes. Change the production line, change the object position, and you're reprogramming and recalibrating everything. Embodied intelligence promises something different. Adaptability. A robot that handles packages of varying sizes, shapes, weights, and materials. Cardboard boxes, soft bags, heavy items, light items, regular shapes, irregular shapes. Packages arriving at random orientations, random positions, possibly stacked or occluded. The robot must use vision to determine what it's looking at, where to grasp, and how to grasp. That's the value. Flexibility in the face of complex, unpredictable tasks. Third, medical and Kung Fu assistance. Healthcare robots for nursing, rehabilitation, and surgery. A nursing robot might deliver items to elderly patients, assist them in standing up, perform basic health checks. A rehabilitation robot guides patients through repetitive recovery exercises. These applications demand extreme safety. The robot isn't just completing a task. It's interacting with a human body. When helping someone stand, the robot must sense body posture, estimate forces, and adjust movements in real time. Move too fast or apply wrong force, and you risk serious injury. Healthcare embodied intelligence must be not only smart, but safe, stable, and reliable. Fourth, autonomous driving. You might think cars and robots are different categories. From an embodied intelligence perspective, they're the same thing. A self-driving car is an intelligent agent with a body, its chassis, its sensors, its actuators. It perceives the environment through cameras, radar, and LiDAR. It understands traffic scenes, lane lines, traffic lights, pedestrians, other vehicles. It makes decisions, accelerate, decelerate, turn, brake, and it executes control, steering wheel, throttle, brakes. The environment is dynamic and complex. Traffic flows constantly. Weather, lighting, and road conditions vary. Autonomous driving is embodied intelligence operating at high speed in high-stakes, real-world environments. Fifth, virtual agents and simulation. A lot of embodied intelligence research doesn't start on real robots. It starts in simulation. The reason is practical. Real robots are expensive. Training through trial and error on real hardware risks damaging expensive equipment and possibly causing safety incidents. Virtual environments give us virtual kitchens, virtual living rooms, virtual warehouses where robots can practice millions of times safely. Simulation generates massive training data, enables rapid validation, and supports diverse scenarios. But here's the catch. Virtual is not real. There's always a gap. Behaviors learned in simulation don't transfer perfectly to physical robots. This is called the sim-to-real gap, and it's one of the hardest open problems in embodied intelligence research. How do you train in simulation and deploy in reality? How do you make the transfer effective? That's a frontier question. Finally, let's address the big picture. Why is embodied intelligence getting so much attention right now? Robots have existed for decades. AI has existed for decades. Industrial robots have been working in factories for years. But embodied intelligence specifically has exploded recently. I see 5 converging forces. 1. Perception technology has matured dramatically. Older robots struggled to understand their environment. Modern computer vision, object detection, and 3D perception have advanced so rapidly that robots can now reliably identify objects, understand scenes, and estimate positions. 2. Large models have transformed AI's capacity for language understanding, task decomposition, and common-sense reasoning. This matters enormously because real human instructions are not precise coordinates. Nobody says move to position X, grasp object Y, transport to location Z. People say, bring me that thing, clean this up, help me with this. Natural, fuzzy, open-ended language. Large models give robots the ability to handle this. 3. Robot hardware has matured and costs are dropping. Motors, mobile bases, dexterous hands, depth cameras, sensors more capable and more affordable every year. This pulls embodied intelligence out of the lab and into practical deployment. 4. Simulation platforms and datasets have become rich and accessible. Embodied intelligence needs enormous amounts of training and testing. Simulation provides safe, low-cost, large-scale training. Rich datasets help models learn better and understand more scenarios. 5. Real-world demand is surging. Industry, logistics, home service, healthcare, autonomous driving. All sectors urgently need more intelligent, more flexible robotic systems. So, embodied intelligence isn't hot because of one magical breakthrough. It's hot because multiple forces are maturing simultaneously. Large models provide the brain. Hardware provides the body. Sensors provide the senses. Simulation provides the training ground. And industry demand pulls everything toward real applications. This convergence is what makes the current moment so significant. Let me close with a single-sentence definition to carry forward. Embodied intelligence is a new AI paradigm where intelligent agents, through physical or virtual bodies, perceive their environment, understand tasks, plan actions, and complete real-world goals through continuous interaction and adaptation. That's what we're here to learn. That's what this field is about. And if you've made it this far, you now have the conceptual foundation. Next, we build on it